All right, so we're starting chapter 6 in Bio 101. Chapter 6 deals with metabolism, and it also deals with enzymes. And so we're actually going to start off with the enzymes, which is the second part of this chapter first. And that's going to be with the test that covers chapters 4 and 5. And the second part of chapter 6 is going to go with chapters 7 and 8 on that test. So let's take a look at enzymes. So enzymes, as we've talked about before, these are organic catalysts. They're going to increase the rate of chemical reactions without themselves being changed. All right. So here's, let's go to this picture here. So this is trying to show, here we have a couple things. We're bringing those together. We get the products out of there, and then this is the enzyme afterwards. It looks exactly the same from start to finish. So the substrates here are what are known as, those are the reactants in the enzymatic reaction. So we call those substrates. And where those substrates bind to is what is known as the active site. So that's the part of the enzyme that binds to the substrate. Now, because that active site has a particular shape, only certain types of molecules can bind to it. And so this is why enzymes only catalyze certain reactions. And so even though lactose and maltose and sucrose are all fairly similar sugars, if you don't make the enzyme lactase, you can't break down the sugar lactose. And that's how people are lactose intolerant. It doesn't matter that you already make the enzymes that break down maltose and sucrose. You need to make a new specific enzyme for lactose. All right, so how enzymes speed up chemical reactions. So the first thing we have to talk about is the energy of activation. And this is the amount of energy that's required to start a chemical reaction. So if we look at this chart, it shows we need this much energy to get this reaction going, all right? And then the reaction can occur on its own after that. Well, what enzymes do is they lower that energy of activation, so that starting amount of energy that we need, okay? So if you think about this, like if you light a match, the match will burn afterwards. So you just had to add that little spark to it. That's the energy of activation. And so by lowering the energy of activation, right, this is going to speed those reactions up, because now you can have two reactions occurring with the same amount of energy that initially you just had one. All right. Now, let's talk about some aids to enzymes. One are cofactors. This is an inorganic substance that is required for the activity of an enzyme. So this is like minerals, so zinc and iron, so things that we need in our diet. Next are coenzymes. Coenzymes are organic substances that are required for activity in an enzyme. And these are vitamins, so vitamin A, vitamin B, vitamin C, stuff like that. All right, so let's look at what affects the enzymatic reaction rate. So one thing that affects the enzymatic reaction rate is just the substrate concentration. How much of those reactants that we have available. So if we have more substrate available, the reaction is going to go faster. And this is all a simple thing, is that in order for an enzyme to cause a reaction, it has to literally bump into the substrate. So if you have more substrate, there's less search time, all right? So also with that, I'm thinking, if we have more enzymes around, so if we increase enzyme concentration, that will too also increase the reaction rate. So there's just more enzymes, we're gonna have a faster reaction rate. The next thing is temperature. So in most of this is going to make intuitive sense. Like if we increase temperature, that's going to increase the reaction rate. All right? And so that will happen. But this will occur until we get to a certain point. And because the thing about enzymes is enzymes are proteins. And one of the things I told you before is that if we heat up a protein too much, we can denature that protein. So change the shape of the protein. So after we get past a critical temperature level, we're actually going to see the reaction rate go down because we've denatured that enzyme. And so this is showing optimal temperature for a typical human enzyme, 37 degrees, that's our body temperature. But after that, we see that the reaction rates slow down. And this is why, 104, 105, 106 degree temperature can be life-threatening. All right? So, this is optimal temperature for an enzyme of a thermophilic. So organisms that like heat, bacteria. So 77 degrees Celsius. So 77 degrees Celsius, we're talking about like 180 degrees Fahrenheit, right? Water boils at 212. All right, so we definitely wouldn't be alive. All right, next is pH. every enzyme has its optimal pH range. Outside of that optimal pH range, that enzyme would denature. So if we go to this next picture, this shows pepsin. So pepsin is an enzyme that works in our stomach. So its optimal pH range is pretty close to 2, right? So, but after we move from our stomach, we go into our small intestine. And the pH in our small intestine is right around 8. So pepsin and trypsin are both enzymes that break down proteins, but this enzyme that's in our stomach is no longer working in our small intestine because it's outside of its optimal pH range. So now let's take a look at regulation of enzyme activity. All right, so here's the thing about enzymes, is an enzyme encounters a substrate, there's going to be a reaction. So an enzyme isn't going to look around and say, oh, look, we have a lot of product here, I'm going to stop working. No, if it encounters a substrate, it's going to cause a reaction. So we have to do other things to prevent an enzyme from working all the time. So how we do this is through what is known as a negative feedback mechanisms. So a negative feedback mechanism is where the product of a chemical reaction is going to inhibit its own production, okay? So think about it this way, your thermostat at home, right? The thermostat is set at a certain temperature. So, when I'm recording this, it's the summertime, so let's say, you have your house thermostat set at 75 degrees. So if it gets warmer than 75 degrees in your house, well, what's going to happen? The thermostat sends a signal to your air conditioner starts to produce cold air, and that gets pumped into the house until when? Until the temperature of the house gets below 75 degrees, and the thermostat shuts off the air conditioner. That's a negative feedback mechanism. The product there, which is the cold air, is eventually going to inhibit its own production. Okay? So, there are two ways in which negative feedback mechanisms are used to inhibit enzyme activity. So the first is through what is known as competitive inhibition. So competitive, there's a competition for the active site in this one. So this is where a molecule, which is typically the product, so a molecule other than the substrate will bind to the enzyme's active site. All right, and that's what we see here. So here's the substrate, here's the competitive inhibitor. It's competing for that active site. And so that competitive inhibitor, most likely it's the product, binds to that active site. That prevents the substrate from binding, and so there's no reaction. The other way is through non-competitive inhibition. And so this is where a molecule, once again, the product, binds to the enzyme, but not at the active site. All right? So it's going to bind somewhere else. But so just like I have to change the shape of my hand to grab onto this red pen, all right, when a molecule binds to another molecule, they're going to change shape as well. And so when this molecule binds to this enzyme, it causes the shape of the enzyme to change, which changes the shape of the active site. And by changing the shape of the active site, that prevents the substrate from binding, and so there's no reaction. Okay? So two ways in which the product can come back and inhibit its own production. One is binding to the active site, and that's competitive inhibition, so they're competing for that active site. The other is non-competitive inhibition, and that's where it binds to the enzyme, but not at the active site. Now, I just want to point out something, right? So this is showing, this with making this end product isoleucine. You can see there's a lot of intermediate reactions that occur to make that product to come back and have that inhibition.